Alright, so here Dan is showing the wood versus steel, just showing our column members that we're going to be using. We've got an oak dowel, and we have the other pine dowel along with our steel rod shown first. So here Dan is going to be buckling the pine member. You can see that he's pushing down with a good bit of force there, and it was buckling. Here the oak dowel, and you can tell that it's taking a little more force but still buckling, relatively easy. And lastly, he's attempting to buckle the steel member, and he cannot buckle it at all. Alright, so here we will be testing the differences in length for columns to buckle. Still the 5/8 inch pine dowel, we've got one 36 inches and the other piece is 12 inches, and we do have another one at 24. Here he's attempting to buckle the 36, and you can see that it's relatively easy. And then we have the 12 inch member here that he cannot get to buckle, as you can see. So here Dan is attempting to buckle the 24-inch dowel, still the pine, and you can see that with a great amount of force, it barely shows any signs of buckling. Right, so here Dan is going to be doing the different cross-sectional areas. We have the round dowel and a square dowel, both 5/8 inch thick. You can see here that the round dowel takes a pretty good bit of force to buckle, and that the square dowel is a little bit easier to buckle. Alright, so here we're trying the different attachments. This one is the fixed. You can see it's fixed there at the bottom in the hole of the platform, and then it's going inside the wooden member he's pushing down on, and it's pretty tough to make buckle there because it's shortening the member. Alright, so here we're going to show a column that is pinned at the bottom, able to rotate, and at the top it is fixed. And you can see this one is relatively easy to buckle. Okay, so here we have a column that is pinned. It can rotate at the bottom and rotate at the top. It's a little easier to hold on to, but Dan felt that it was tending to buckle a little easier. Okay, so here we're going to be demonstrating a column that is braced at midpoint compared to one that isn't. Here you can see that it buckles relatively easily there. And then once you put it through the midpoint bracing, you will see that the column acts as two shorter columns, making it much more difficult to buckle.
Shown here, we're going to solve Euler's equation. P is the force at which the column buckles, L is the length of the column, E is for modulus of elasticity, and I is the area moment of inertia. These are the formulas for the area moment of inertia for both the rectangular and the circle cross sections. Here we have Euler's equation for the steel with the circular cross section. Steel has a modulus of elasticity of 29 million and an area moment of inertia of 0.0074901,406. And here they are shown worked out for lengths of 48, 36, 24, and 12. These are the Euler equations for the wooden dowel with the circular cross section that has the same area moment of inertia, but a modulus of elasticity of 1,595,000. And these are the different lengths: 48, 36, 24, and 12. Here's the steel dowel with a squared or rectangular cross section. Modulus of elasticity is still at 29 million, but the area moment of inertia is 0.0127156,576. And these equations are worked out for the lengths of 48, 36, 24, and 12. Shown here are the Euler buckling equations for the wooden dowel with the square cross section. We have the modulus of elasticity of 1,595,000.